Hello everyone, welcome back to 3 Deviations. In today's video of single variable calculus, I'd like to talk about the integral of the natural logarithm. Now, I said in the last time we will be moving on to trigonometric reduction, but I wanted to fit this in because this is something important that we should be covering on these videos. This kind of introduces a new kind of thing that we use to our advantage in integration by parts, and we'll be explaining that as we go along, but it's something that is pretty helpful and I find pretty funny that it works, and it's pretty nice. Alright, so let's talk about the integral of the natural logarithm. Okay, so here's our example. We're just going to be taking the integral of the natural logarithm. So when I say that I want you to take the antiderivative of ln x dx, well, you're kind of stuck because there's no real integration technique that we know that's going to help us with this. I mean, I said earlier that we're going to be using integration by parts for this, but how? If I look through, there's no just rule that says the integral of the natural logarithm of x equals something. We can't do a substitution here because there's no other thing to substitute. We're really kind of stuck. So this is what our plan is. We're going to do something that I really think is quite funny, as I said earlier, but instead of writing this as the natural logarithm of x, we're going to write this as the integral of the natural logarithm of x times 1 dx. Now, obviously, this is the same thing as the integral of the natural logarithm of x, but now we're just writing it as a product of functions. And I mean, 1 is it's a scalar quantity, but it's still a product nonetheless. So now we can apply integration by parts. If we go back to the Liate convention, so if I have Liate, then we're going to be differentiating this natural logarithm of x because that's a logarithm, and then this algebraic term is 1, so we'll be integrating that, and that's going to become x, and that's going to make our job for integrating a little bit easier. Okay, so now let's plug into our bracket here. So we're going to get u is equal to the natural logarithm of x, du is then equal to 1 over x, the derivative, times our differential dx. dv will be equal to 1 dx, and then v will be equal to the integral of 1 dx, which is x. So now we get, when we plug in, we do uv, so that's x times the natural logarithm of x, minus the integral of v du, which is x times 1 over x dx, which is just x over x, which can be simplified to 1. So this gives us x times the natural logarithm of x minus the integral of dx, which of course is equal to x ln x minus x plus c. Okay, so now we have our final answer, and that's how we deal with this. So if you're ever thinking that you have a function that reduces really nicely, usually this the logarithm and the inverse trig work really nice with this method, but just write it times 1. If you just have one of these guys, write it times 1, and then you'll be good. Okay, so now I'd like to kind of do just one more example before we move to trigonometric reduction. It's always good. So we're going to be visiting our old friend of average value of a function. This is from James Stewart's Early Transcendentals 8th edition from section 7.1, example number 66. Okay, so I want us to determine the average value of x secant squared x on the interval between 0 and pi over 4. Okay, now x secant squared of x, that is quite the big function. So we are going to be integrating that. And if we remember that our formula for average value, f of a is equal to 1 over b minus a times the integral from a to b of f of x dx. So we're going to be doing some definite integration here, but that's okay. So what we do is we plug this in. So if I do 1 over b minus a, 1 over b minus a, we get 1 over pi over 4 minus 0, which is really just 1 over pi over 4. So we really just get 4 over pi. So you get 4 over pi times the integral between 0 and pi over 4 of x secant squared x dx. Okay, so we're obviously going to need to do an integration by parts. Our Liate convention says that we take the algebraic term and we differentiate that. Of course, x goes to 1. We should know that by now. And then we've got the trig term, so that wants to be our dv. So we've got u equals x, du equals 1 dx, dv equals secant squared of x dx. And of course, secant squared of x, we know that as the derivative of the tangent, so v equals the tangent. Okay, so this gives us, so we are going to get from here, I'm just writing down here a derivation for the tangent, which we're going to be using later. But from here, if we do our little cross thing with our table, we're going to get x tangent of x minus the, and that's evaluated between 0 and pi over 4, and all of this is multiplied by 4 over pi. So x tangent of x minus the integral between 0 and pi over 4 of, then we do v du, so then that's going to be the tangent of x dx. Okay, so we haven't really talked about the integral of the tangent, so again, that's why I'm deriving it down here. Of course, we can close that parenthesis. So the way that we integrate the tangent, so this is something that would probably be on your test formula, but we'll derive it here. So we get the integral of the tangent of x dx is equal to the integral between, or the integral of the sine over the cosine, right? Because the tangent is equal to the sine over the cosine. Okay, so now we can perform a substitution. You might be able to do this in your head. We set u equal to cosine of x, du is equal to negative sine of x dx. This gives us the integral of negative du over u, which becomes negative natural log of cosine of x plus c, or of course, you could rewrite that as the logarithm, natural logarithm of the absolute value of secant of x plus c. You can put in the logarithm of identities and change the cosine to a secant and remove the negative sign if you want. Okay, so now all that's left is we are going to be evaluating the fundamental theorem of calculus. Sorry, I kind of written over what I wanted to talk about, but when we evaluate this, we're going to get the product. So we're going to get 4 over pi times x tangent of x, evaluated between 0 and pi over 4, plus the natural logarithm of the cosine of x, evaluated between 0 and pi over 4. And that's equal to 4 over pi times pi over 4 minus 1/2 natural log of 2. And that simplifies to 1 minus 2 times the natural log of 2 over pi. So that's the average value of the function in the domain here that we